if you go to the schedule on the website, to this and click here, and oh no, you go to this and then you click down here on resources. This website here is not the right website at all. Sorry. Okay, this is the URL. I'll Slack it as well. neurohackademy.github.io/convolutional-neural-networks is the right URL. Let me Slack that into general. Let me move this thing out of the way, and I'm going to run this all on our hub. Let me just close up let me move here slightly so that I can see what I'm doing. Flat screen. Okay. Good. Okay, so the link is in the Slack in general. Yeah, I Slacked it in general. That's the link to the materials. So I'll just mention that the materials are written in this kind of website form that we borrowed from software carpentry. So the episodes include things like things with code. So it's not really notebook format, but I will be running things in the notebook, and the hope is that when I write stuff, it'll be slow enough so that you can write along as I go. So instead of running through a lot of cells, I'll be typing along together with you. The goal here is to slow me down a little bit. Okay, so let me get started. So the goal of this tutorial is to teach you a little bit about convolutional neural networks and how to use a software package called Keras to train neural networks, evaluate them, use them for inference, and so on. This is going to be like the tip of the iceberg of a very large topic, and the goal is really to give you a little bit of an intuitive understanding of what neural networks do. Without going into a lot of the math behind it. Instead, I'm going to try to explain the math behind training neural networks using a little bit of simple code. So the first part will be, I'll show you the world's simplest neural network, and we'll train that up using the same kind of machinery that Keras uses under the hood. And then we'll go to Keras and show how we implement that there as well. And like I said, I'll go until 6:15. And then we'll break and go to the poster session. And if there will be stuff left, and undoubtedly there will be stuff left, we can add stuff, kind of go over other stuff later in the week or next week. Okay. So just to set the stage, neural networks have become really popular in recent years, and they've been around for a really long time. Is part of what might be puzzling. The ideas behind the neural networks that people use today in many different applications, those ideas stem from ideas that really were there at the beginning of computing. I heard a talk by somebody, Blaise Aguirre-Acras gave a talk, and he described how computing and neuroscience were twins that were separated at birth and now have come back together in neural networks. And really, when you look at papers from the beginning of neuroscience, there were ideas that were there and they propagated through. But so why are they so popular today? Well, there are a few factors that added to this. The first is development of technologies, in particular hardware and software that can implement very large neural networks. Chief to these ideas or to these kind of developments are the use of graphical processing units to do some of the algebra behind the neural networks. And that just makes things go really fast so that you can do things that were just unrealistic a few years ago. The other is the availability of really large data sets to work with. Neural networks, especially very large neural networks that work really well, have a ton of parameters, and we'll talk about that in a few minutes. So they require a lot of data to train. And so before just a few years ago, there just weren't the kinds of data sets that you need in order to train neural networks effectively. And then, not least, there were a set of theoretical developments across a range of different fields, ranging from optimization and also sort of within neural networks, the field itself, that led to it being practical to do a lot of the things that just weren't possible a few years ago. So it became practical only quite recently. I think a watershed moment in this is 2012, when an algorithm that uses a neural network won the so-called ImageNet challenge. ImageNet is this big data set that includes millions of images of 1,000 different classes of natural objects. And until 2012, the leading algorithms in performance in identifying these objects were algorithms for classical machine vision or computer vision. And in 2012, Alex Khrushchevsky and colleagues proposed the neural network that won that challenge, and ever since then, neural networks have dominated that to the point where now the most recent results in this are pretty much as good as humans in doing this task. Actually, one of the researchers who was very active in proposing those tested this by doing this himself on a lot of images and just measuring his own error rate in this and showing that it's similar to the neural network. Okay, so what does a neural network do? How does it work? So here's a simple neural network. It's in there in the. This is the world's simplest neural network. It has 2 input nodes, x11 and x12, and 1 output node, x21. The subscript denotes, the first subscript, 1 here, denotes the layer. So we have 2 layers here. And the second subscript denotes the identity within the layer. So this is x11 and this is x12. This is x2 because it's the second layer and there's only one, so it's x21. And then the weights between this, so this unit impinges on this unit with a weight, w11 superscript 2. So the superscript here indicates the layer that this impinges on, and the subscript indicates that we're going from unit 1 to unit 1 here. So this is w superscript 211, and this is w2, so to the second layer, from unit 2 to unit 1, 21. Okay, so that's sort of the conventions that we're gonna follow here. Let me move this out of the way so I can implement this in code now. Okay, so here it goes. x11, oh no, x equals. I'm just going to choose some arbitrary value for the inputs. W211 equals -2, and some arbitrary values for the weights. So this is sort of our starting conditions for this network. I've initialized the activities in the input units. Imagine that this is an image with 2 pixels. 1 pixel has the value 1, 1 pixel has the value 2. And then the weights onto this other network, they can be negative, they can be positive, and so on. The way that the output layer computes its value is by taking the weight onto layer 2 from unit 1 to unit 1 times the activity in unit 1 plus the other weight times x12. And I had a typo here. Like that. Okay, good. So if we look at this, it's equal to 4. That's the answer here. Sorry, I can't hear you.
Could you tell us what the subscripts and superscripts?
Yes. So this is the first unit in the first layer, and this is the unit in the first layer that is the first, x11, and then this is the unit in the first layer that is the second, x12. So those are both in the first layer. And this is the weight onto layer 2 from unit 1 in layer 1 to unit 1 in layer 2. And this is the weight onto layer 2 from the unit that is the second in layer 1 onto the first unit in, oops, that inverted that, onto the first unit in the second layer. And then this is how we calculate the thing. It's a dot product between the inputs and the weights. So we can rewrite this as a dot product. x21 equals np dot, I should import numpy as np. np dot W211, W221, X11, X21, 1, 2, sorry. Okay, so this calculates the same thing. It's also 4. So this and this are the same calculation. I'm just so this is linear algebra. It's you can think of this as also as a linear regression. It's the same equation as you would have for a linear regression, right? So this is linear regression so far. Let's look at a slightly more complicated network. Let me put it up on the screen first and then implement it. So this one has one layer, and then it has weights, and it has first layer down here. That might be the pixels in the image, and then there's 2 units in the second layer, and then there's a third layer with 1 output unit. So it's only slightly more complicated. So there are 4 weights in the intermediate step, and then 2 weights here towards the output. So let's write that one in code. Okay, x11 equals 1, x12 equals 2, that's the input, and then w211 equals -2, w221 equals 3, w212 equals 2, w222 equals -3. And then we have more weights, w311 equals 3, w321 equals 2. So okay, so now we have the 2 layers. These are the 4 weights from the first layer to the second layer. They all impinge on layer number 2, so the first subscript is, or this is the kind of the superscript as I showed it before, is 2. And then this is from the first unit to the first unit. This is from the second unit to the first unit. This is from the first unit to the second unit, or from the second unit to the second unit. And then we have the same structure that we had before for the last layer. We have, and then now it's layer 3, from the first unit to the first unit, and from the second unit to the first unit. So we start these initial conditions, and then now the calculation is x21 equals np dot w211 w221 x11 x12 x22 equals np dot. So we collect for every unit in the intermediate layer, we collect its inputs from the first layer, and then we can calculate x31 is the only unit there. It's np dot w3 11 w3 21 x21. Okay, and then the output is x31 is 4. It happens to be the same number as it was before, but that's not actually necessary. Let me change one of these weights here just to demonstrate that that doesn't have to be the case. There we go. Okay. So now the output is there's linear regression happening here, and there's linear regression happening here, and linear regression happening here. We might be able to collapse that all into one linear regression. Things get a little bit more interesting if, in addition to this computation, we add some kind of nonlinear function on the outputs of every one of these units. So in the intermediate units, we might say, well, we've computed a dot product on the inputs, and now before we output this to the next thing, we'll run this through some kind of nonlinear function. That nonlinearity gives these a lot of computational power. One of the nonlinearities that's really popular and should be familiar to neuroscientists is this one. So NPA range. Let's take AX, some kind of range of values, and NP dot. We'll take a range of values from pi to NP dot pi. We'll take really small steps, so we get a nice. And then the function I oh, I need to import matplotlib dot pyplot as plt, and so I'm importing matplotlib so that I can plot this for you so that you see what this looks like. And doing that magic matplotlib inline makes sure that the figure appears in the notebook inline. Plot amp dot x versus np dot tan h of x. So the hyperbolic tangent is one nonlinearity that was very came immediately to mind to people who designed these things in the 50s and 60s, because this looks a lot like the FI curve, the response function of a neuron, right? There's a threshold down here. There's some kind of threshold behavior, and then it saturates when it can't fire anymore. And this gives neurons interesting properties. You can think of these curves being distributed along a range. You can create a whole population of neurons that does really interesting, can encode really interesting things using these kinds of nonlinearities. What happened along the way is that people figured out that you can simplify this a lot. So one of the ways that people simplified this is, instead of using this kind of hyperbolic tangent, they use something called ReLU, or rectified linear unit. This looks very similar to this, but the implementation is slightly different. I'll show you what that looks like in just a second, but let me just implement it first for you. It returns the maximum of x and np dot zeros of the shape of x on the 0th dimension, and we're taking the axis equals 0 here. This might look a little bit weird, but let me just show you what it does, and then it'll be a little bit. So I'm plotting x against ReLU of x, and then it should be a little bit easier to understand. What this does is it rectifies everything that's below 0. So whenever x is negative, it sets it to 0. And whenever it's larger than 0, it sets it to that value. So it returns to you either 0 or the value of x, depending on whether x is negative, in which case it'll be 0, or positive, in which case it will return x. And I've implemented this here using a maximum function, taking the maximum between x and 0 at every point. This is called a rectified linear unit, and people have used this one, and you'll see in just a couple of minutes, you'll see why this is actually not a bad idea. So now our neural network that we saw before becomes the following: x21 equals ReLU over np dot w21 w221 and x11 x12. And did I get all my parentheses? I do. x22 equals ReLU of w221 w22. Whoop. Okay, so that's the entire network now. It's yes, I do. Thank you. There you go. Okay, so it looks the same as before, but I've added ReLU before every line, so that every output of every computation goes through this rectified linear unit, and then there's an indexing error here somewhere. Huh, that's fascinating. So there's an error in the. Huh. Zero-shaped things. It's a single number. That's interesting. Sorry, I'm using debug. Debug is a magic that allows me to drop into where that error happened and figure out what happened. Which is not fun while you're trying to teach something that you thought works, but. Oh, I don't need this ReLU here, sorry. No ReLU at the end. That was not it. Let me run this initialization code again and hope that that was all that, no. What if I did this? Whoop. Sorry, no, that actually worked. So now I took the, so I seem to have stumbled over myself just a little bit here, but oh, I know. Kernel restart. Restart. Kernel restart and run all cells. Okay, so this does, and I'll put a ReLU right here because why not? Yeah, so the reason that this went wrong was that I had, when I plotted, I had an array, but when I was running the network, I didn't have an array, I had a number. So referring to the shape of that number didn't work. Sorry about that. Okay, so this is nice. So now we can do, the nice thing about this is that it gives the network power to compute things that are fairly nonlinear. One way to think about what neural networks do is that they take and they map from one domain, say the pixels in an image, to something that's quite different, like the space of all the categories of objects. And to do that, you need to kind of bend things. You need to bend that space gradually so that when you end up over here, the representation is quite different from where you started, such that now you can neatly separate different objects, for example. That's one way to think about the math. And doing these nonlinear operations on the inputs allows you to sort of twist the shape gradually. And the more layers you have, the more you kind of twist in stages until you reach a point where you can kind of cut between these things. Jim DiCarlo, who's a neuroscientist, again, has written quite elegant papers about this idea and how it works in our visual system. This idea that we take the pixels that come, or the activations of our retinal ganglion cells, and how our ventral stream does these small nonlinear transformations until we reach a point where in IT cortex, it's just objects because we've kind of changed the space gradually into the space where we can separate between objects. That's what these nonlinear operations are supposed to give us here. If that was not 100% clear, just wait a little bit until we get in and look at a concrete example of that. Okay, let's talk about training the network. So how do we learn what the right weights are? So the typical situation that we'll be facing here is that we'll get samples for training. We'll get inputs, 2 pixels of the image in this case, and then we'll get outputs, some number, any kind of real number, and we'll be training the network. We'll run the pixels through the network, and we'll get some answer from the network, and we'll compare the answer from the network to the real thing. That'll be our training sample. We'll compare those two to each other and say, oh, there's an error. Let's say that we think that this particular network right now should return the number. Let's say the desired output was 10 instead of this 12. Then our error is 2, right? Our desired output is 10, but we got 12, and we can compare those to each other and say the error is, well, let's do the opposite way around. There's an error of 2. It doesn't really matter in which direction you go. So, we can calculate an error for the activation of 3.1 by saying that'll be the activity of 3.1 minus the desired output. Let's say that for this image that we're showing with these 2 pixel values, we know that the answer should be a 10. But it came out to be something else. We can calculate that error as 3.1. And then the process that we will use in order to train the network is called backpropagation. And so backpropagation does the following thing. It propagates the error from the top of the network. We think of this activity right here as the top of the network back down, and at every step it will adjust the weights based on this process of backpropagation. So for every weight, it will calculate some kind of change, gradient or a derivative, or some kind of change that needs to happen by multiplying the following three numbers. The three numbers are the gradient of the loss function with respect to the node a weight feeds into. So in this case, it will be this thing. This is our loss function. So we'll with respect to the weight, so when we're thinking about weights going into x31, the two weights that go into that last node, their error of the loss function is this thing. We'll see how that propagates back. And then the second thing is the value of the node that feeds into that weight, right? So for this case, that'll be the weight, for example, for the weight from the first unit, it'll be the activity in the first unit in the second layer. And then the slope of the activation function of the node it feeds into. So the slope of the activation function is the slope of that nonlinear function. So this is I'll actually write the code that calculates that last factor. And I'll repeat those factors in just a second. I'll just show you the first thing. This is the slope of the activation function of the node the weight feeds into is the slope of the rel u function. And that has two possible values. If x is larger than 0, that slope is 1. And if otherwise, if it's 0 or smaller, then there is no slope, right? Because at that point, it's all horizontal, so we return 0. That's one reason to use ReLU, because the derivative of the ReLU is dead simple. It's either 1 or it's 0, depending on the input. Okay, let's propagate this error. So I'll show you how this works. So the error for 311, that's the weight, the error for the weight onto the third layer from unit 1 in the second layer to that unit, the single unit in there, is equal to E31. I'm propagating this error up here back times x21. That's the activation of the unit feeding into that weight times d-ReLU for x31. The derivative of this nonlinear activation function with respect to the output of this unit. E321 equals to E31 times x22 times d-ReLU x31. This is the same, but for the other weight onto the first layer, or the only layer in that last unit. Now we're taking the activation of the weight, the unit that feeds into this weight. It's x22. It's the second unit in that intermediate layer. Okay, now we're propagating the error back to the second layer, the weights that feed into the second layer, into that intermediate layer. And that will be equal to the error 311. It's this error. We're propagating this error back. So now you see how the error propagates back from the top. Here we start with the error with respect to the output. In the second layer, we'll go and we'll take this error that we've calculated out of these multiplications and propagate that back. So E311 times x11 times d-ReLU x21 E21 equals E311 times x12 times d-ReLU x. Whoop. Yes, and then E212 equals, so there's two sets of weights in the intermediate layer, so we have to calculate a few more here. We're propagating again, now we're propagating this error back, right? Because we're talking about the weights onto the second layer in the second unit in the second layer. E321 times x11 yes, times d-ReLU x22 E222 equals E321 times x12 times d review x22. Okay, so this, we're propagating, so we start here from the top, calculating the error with respect to the output. We go and we calculate the errors for the weights onto that output unit with respect to their activity, the activity of the units impinging on there, and this error that we propagated from the top, and then the derivative of the loss function with respect to the outputs of this unit. And we do the same for every one of the other weights in this entire network. And so now we have all the errors for all these weights. Now we correct for these errors. So to correct for these errors, we need to change each one of these weights by a small step in this direction, in the direction of correcting this error. So take a small step. We set a learning rate equal to 0.01, and then we say, okay, W311 is equal to W311 minus the error for 311 times the learning rate. W321 equals W311 minus E321 times learning rate, and so on for the others. Okay, I'm gonna, and for the sake of time, I'm gonna copy and paste. What this does is it takes these errors and it applies the negative of that error times some small step on each of these weights. So it adjusts each one of its weights by how much error that weight has. So we have this whole series of weights, right? And each one is moving a little bit. So you can think of that as taking a little step. So imagine that we're looking at the error, the value of the error in space that is where each dimension is the value of one of these weights. What we're doing is we're taking a tiny little step in that big space to reduce the error a little bit. Think of this, imagine that we're thinking about only two weights. You can imagine there's a hill here, and that's the error, and we're walking down that hill. But we're doing this in this case in, 6 dimensions. And in the case of really large networks, in the space of some million something, or actually 32 million in some cases, dimensions, we're taking a tiny little step, and we're trying to find a basin, a good basin, the global maximum, if possible, in this big thing. If it was only 2 dimensions and this was well behaved, that would be easy, but it's 32 million dimensional, and who knows if we started even close to the global minimum of this function, so it becomes hard. But this is the same operation that those really large neural networks do. And so we can then ask, what happens if we apply the neural network again? So we apply the neural network, and then look, okay, we've gotten closer to our desired answer. We're at 10.5. Let's do this again, this whole operation again. We backpropagate the error, we adjust the weights, and we go back here and calculate this again. We're even closer. So we keep getting closer to our desired answer, and at some point we decide that we've reached close enough to where the answer is correct, and we stop. Now we do this actually, here I've done it, it's a little bit contrived. I'm showing the same training sample again and again, only one training sample. Input is inputs, with the output is supposed to be 10 and we're getting closer. But imagine that we show the network different combinations. We show it a 2-pixel image and then 10. This one should be 10 and this one should be 12 and this one should be 14. And we keep doing this. The principle is the same. We keep, for every round, we adjust the weights and we go over all the data that we have. And we keep training like that. And then once we've gone through all the data that we have, we go back to the top and we start again, and we run it through all the data again. And that entire going through the data is called an epoch of training. And there's a way for us to actually feed multiple, we can do this by feeding multiple samples into the network each time, and we call that a batch. So the batch size will be how many images of 2 pixels matched to the real answer do we give it. That'll be the batch size. We take up, let's say we have 100 images, we divide it up into 10 batches of 10 images each. We feed it 10 images, we do this training, this backpropagation, adjust the weights, then feed it another 10 images, and adjust, and so on 10 times. We've gone through the data. That's one epoch And we repeat that again, and we repeat that again and again, and so on, until this converges or until we've reached some desirable outcome. I'll show you how we verify that a desired outcome has been achieved. So that's the general principle. And this applies, I think, for most neural networks that we use in practice. What questions do you have at this point? Yes?
How does the layering aspects work, like deciding how many layers to add in? Or is that too?
So that can be an empirical question. Let me show you how you start layering stuff, and then we can talk about 1 layer versus 2 layer first, and then go from there on. Okay.
So the epoch versus the batch.
So say that again?
So the distinction between an epoch and the batch.
An epoch is one time that the network has seen all of the data that we have for training. And a batch is how many samples do you give it each time you train it?
Why don't you give all the sample at a time?
Just like one sample at a time or all the entire thing? That's a little bit about kind of the accuracy of what you're trying to do. There's a trade-off, right? If you show it all of the things together, then you might have different things that are pointing to different directions, and you might kind of learn very slowly. On the other hand, if you show it just one thing at a time, each thing has its own sort of effect, and it'll throw you in different directions each time. So that's kind of the trade-off, and you want something in between those two. Does that make sense? Okay. Let me go and actually do something here. So I realized that I have some data in here that I would like to. Oh yes, the data is in. I think it's in data. Let's try this. LS data. No. Where did I put it? Oh, you're getting to see all the things. No. Yeah, no, I'm sorry. I just realized that I have some data that I'd like to use, but that I failed to put in the right place now. So let me upload it from my own machine, and then you'll have to just look at me doing this, and then I could give you this data later on. Actually, given the timing, I suggest that we take this as part 1, and we will find a time to do part 2, where I'll show you. So I've shown you sort of very basic principles so far, and I'd like to actually show you Keras, which I promised to show. But since it is almost 6, let's maybe break here, and then hopefully tomorrow at some point, or the day after, there will be a time to do part 2 of this very tutorial. Okay, but then I will have found where the data is and put it up where you can get it as well. Okay. If that's agreeable, then we'll break here now, and then we have dinner actually in 5 minutes, which is very apt. So you can all go put up your stuff in your rooms and so on, and get organized. If you have a poster, this is it. So there are poster boards out there. Bring your posters down from your rooms or wherever you have them, and set them up on the poster boards. We don't have necessarily a particular place for each one of you, but find a poster board that doesn't have a poster on it, and put your poster on it. And we'll have dinner, and then we'll come in and go and stand by your poster, and we'll come and hear what you're up to. Okay. And now, back to this. Okay. So yesterday, where we left off was I was going to get some data, and now I know where it is. So the data, the materials for this tutorial are all on this website. Oh, where is it? Here, nope. This website, which I linked to yesterday. So if you go here, you'll see the episodes. We've gone basically over the first 15 minutes of this planned thing. There's some timing here that it's not quite accurate. And then if you put a slash and setup here, it will take you to this page that talks about getting the data. And if you click here, it will download a little NPZ file to your machine. And you can get that into your hub by doing, by clicking on this button, upload. In my case, it's in my downloads folder. I hit that, and it shows up here inside the hub. So this is actually useful just in general if you want to get data into the hub. This is a way to get data into your pod on the hub. If you have some data on your laptop that you want to analyze in the hub, that would be the way to do that. And there's a Files tab here. In the Files tab, click this Upload and then upload the data. Okay, let's recap a little bit of what we did yesterday, and then we'll go into today's materials. Yesterday I showed you, the very simplest version of neural networks that we can write down. We started with a neural network with really just one layer, or one layer of connections between two inputs and an output. And I showed you that, and that looks a lot like linear regression. And then we added another layer, and that looks a little bit less like linear regression. And if you add nonlinear functions in every one of the units, it's even less like linear regression. But you can still think, okay, there's inputs, there's then an output. It has a similar feeling, and that's no coincidence. It's a very similar kind of set of machinery, but it becomes really, really complicated. You need to somehow learn all these weights. And what I demonstrated with code yesterday is the algorithm that is used by neural networks in general to learn these weights, and it's called backpropagation. The idea is you propagate the error from the top of the network. We think of the output as the top, down through the layers, all the way down and through all these weights, and you learn them incrementally. And the algorithm that is used typically to do that is called stochastic gradient descent. Gradient descent is exactly this process by which we start at some point. I describe this as a hill maybe, and if there are two weights, you might think of this as a two-dimensional or a three-dimensional hill. You start up here, and gradient descent means that you find in every point a direction. That direction is the gradient, and then you descend down in the error until you find some place where the error is as small as it can be, and you look around and you try to find a gradient, and there is no gradient to go up. Now take this two-dimensional picture and expand it in dimensionality to 32 million dimensions, and you have more or less backpropagation as it is in neural networks. So that's gradient descent. The stochastic part is that every time that we do this process, we choose some chunk of the data. And we call that chunk a batch. So we do this with one batch, and we do this with another batch, and so on. We choose from the data batches, say, of 10 each time. And if we have 120 different items in our training set, we'll do this 12 times. And that will be called an epoch of learning. And by the time we're done with this epoch of learning, depending on the rate at which we're doing this, we may or may not be done yet. We may think that there's more, we could go more. And so we start again. We choose another 10, and we do this again, and we run through the entire data, and we call that the second epoch, and so on, and we repeat that operation until we're happy. And we'll talk about how we know that we're happy with what we have. So that's the general plan. And now I'll show you how that's implemented in a software library called Keras. For the purpose of that, I'm going to use this data that I just imported. Let's look at this data. So I have, if I do, if I type ls, I'll see that I have this NPZ file right here called fashion. This is taken from a data set called the fashion MNIST data set. The reason it's called the fashion MNIST data set is that it's based on a previous data set that people have used for many, many years, the MNIST handwritten digits data set. The handwritten digits, who here has used the handwritten digits for anything, has seen the handwritten digits? Okay, it's a collection of images. They're 28 by 28 pixels, and they have handwritten digits in them, and those are labeled so we can use them for training. For example, for training a classification algorithm, we can say, hey, we want a neural network or some kind of algorithm that knows which digit is in the image, that learns to discriminate, classify these different images. And over the years, people have used this a lot. Some of the earliest demonstrations of convolutional neural networks, which I'll tell you about in just a minute, were using this approach, this particular data set, and it's really useful if you're trying to read checks, if you're an ATM and you're trying to read checks, or you're the postal office and you're trying to read zip codes on envelopes. If you can do that, that's really, really great. But it turns out that data set has a lot of issues. For example, there are certain classifications, certain discriminations that you can do based on just one pixel, the intensity of one pixel. So there's certain, I don't remember exactly which ones those are, but if you wanted to discriminate, just as an example, I'm not sure this is between 0 and 7, you might look at one single pixel, and that would be enough to do a pretty good job at discriminating those two. And people have had a lot of complaints. In addition, a lot of the early work in the field was using this one data set, and what if it doesn't work beyond that? And so people have come up with other data sets, and I mentioned ImageNet yesterday, and this data set is kind of nice because it has a lot of similar characteristics to the MNIST data set, but it's different. It has, instead of having handwritten digits, it has images of clothing, of different kinds of clothing. So let me load this data and show you what that looks like. So to load this, I do import numpy as np, and then fashion equals np.load fashion.npz. NPZ is a special format that NumPy has that compresses, you can compress several arrays into one file. So if you had several NumPy arrays and you saved them into an NPZ file, you can now kind of decompress out the data from that. I'll show you how that's done. So in fashion, we might have train data equals fashion train data, train labels, fashion. And then we'll have a test set as well. Test data equals fashion. Okay, so this object in here, this NPZ object, behaves a little bit like a dictionary in that we can address it with these squared brackets indexes with strings, and it pulls out. So let's look at, for example, train data dot shape. So the way this data is organized is there are 600 images. Each image is 28 pixels by 28, just like the handwritten digits. And there's a 1 here at the end, and that's because when we represent images, we might represent them as either images with only a single channel of information, black and white images, or maybe R, G, and B, red, green, and blue. So that number would be 3 if we had red, green, and blue. So we want to know, because neural networks, sometimes they operate on images with color, sometimes they don't, and so we want to keep track of that. So we keep that 1 in the end there. So that's the train data, and then let's look at the train labels. The train labels is an array with 600 items in it, 600 rows, and 3 columns. And it's organized as what's called the one-hot encoded array. Train labels, I'll just print out a little bit. The way this is organized is rows where every row is one of these images, and the columns are set to 0 for some of the columns and 1 for the column representing that item of clothing. So for example, I don't exactly remember. If we did import matplotlib.pyplot as plt and then matplotlib inline, we can, if we do that, we can take a look at one of these images, matShow train data. So we take a look at the very first one. Will that work? It won't. It actually wants us to take just, matShow requires 2-dimensional things, so I'm going to take all the columns, all of the rows in the first channel, right? There's this one channel in there. So there we go. So okay. So what I learned for that, this is a picture of a dress. It's pretty low resolution, but still we can tell that it's a dress from looking at it. And that means that second column here represents dresses. So when the second column is set to 1, that signifies, that labels for us a dress. If 0, let's plot a few of these. So for in range, let's print out 10 of these. Let's do fig x equals plt.subplots 1. I'll explain this in just a second. Train labels. And then x dot matShow train data im all columns, all rows, 0. Okay, so what I'm doing is, this is a way to create plots in matplotlib. The subplots command, when it takes 1 as an input, it creates a single subplot in a figure, and it gives you back the handle to that figure and the handle to that axis. And in matplotlib, the axes are the things that actually generate the images within them using commands like setTitle and matShow. There are a variety of different commands in here, like plot and hist for histograms and bar for bar plots and so on. So what I'm doing is I'm setting the title to be from the labels and the image itself, so I can take a look at some of these. Okay, so this is the first. This is the same sample that we saw before. 010 is a dress. 010 is another dress. 010 is another dress, and then we have 100 is a T-shirt. And then we have 001 is a shoe. So I've taken out of this data and I've extracted just 3 classes of clothing, shoes, dresses, and T-shirts. And you can see there are a few more of these in here: shirts, T-shirts, shoes, and so on. Good. So that's kind of the data that we're dealing with. So let's start building neural networks to do this classification. I'm going to import from Keras .models. I'm going to import something called sequential. All the models we'll see today are sequential models, like the ones that we saw yesterday. There are models that have the sort of non-sequential things that loop around back and so on, but we won't look at those today at all. We'll only look at sequential models from Keras. Layers, import, dense. So, and we're getting what's called dense layers. When I imported Keras, you saw that it threw up this message. Keras is an API that allows you to use different kinds of backends. And here it's using as its sort of computational engine under the hood. It's using the TensorFlow library. It can use other libraries as well. It can use Theano, which is another library that does very similar things to what TensorFlow does. Just briefly, both of these libraries, what they do is they look at what's in there inside these neural networks once you design them, and they kind of compile a little program for how to train this network. So both of those libraries do that under the hood for Keras. Here we're choosing TensorFlow to do that kind of all the detailed operations for us. Yes?
Together with PyTorch as well?
No, I don't think so. Yeah, so I'll just kind of take off on that and just tell you that the world is a complicated place. And right now, if you want to do deep learning you have to make choices about what technology to use, and there are several different options, including, as you mentioned, PyTorch, which is not necessarily compatible in terms of what it does to this. It does many of the things that this does, and there's more. There's something called MXNet. All of those come out of big technology companies. So TensorFlow is out of Google, developed by Google. PyTorch is developed by Facebook. MXNet developed by Amazon. And for a variety of reasons, they don't just, including that they're competitors, they don't just merge all of these things together into one great thing. Yet another advantage of the sort of open source community that doesn't belong to a particular entity. I should say it's great that they've sort of jumped the open source bandwagon, because we benefit from our ability to use these great technologies that they're developing. And that's a more recent thing. They didn't used to do this, so they've realized that this is a good idea in the recent past and started doing that. So yeah, so all of the things they'll show you today can be implemented in other frameworks, and depending on what you want to do exactly, you'll need to look and assess and choose between those. Okay, so I've also imported a dense layer object. The dense layer object is the kind of thing that we saw yesterday. It's a layer that has connections to every item in the previous layer. Every unit in the previous layer is connected through a weight. So the networks we saw yesterday, there was from the first layer to the second layer, for example, in the 3-layer thing, there were weights connecting between every unit and every unit. And this is the kind of connection that we'll see here. We'll see another variation on this in just a minute. But for now, let's use the dense layers. Now, to use dense layers don't care about the fact that the image has structure. We're going to have a weight to the units in the first layer. We're going to have a weight from every single pixel. And so it actually, for every observation, for every item in the training set, it wants a single row in a matrix. It wants a two-dimensional matrix with rows representing items, like one single observation, and columns representing pixels. So what I have to do is I have to convert this by doing train data 1D equals train data dot reshape. So I have to reshape into this you remember it had 600 items, and each item had 28 pixels by 28 pixels. I have to flatten out those 28 pixels. So I have to do train data.shape. So the new shape that this thing will have is train data.shape by -1. This is I'll explain that in just a second, what that -1 is. I'll just do train test data 1D. I'll do the same thing for the test data. While I'm at it, reshape. Oh, sorry, this should be shape 0 and -1. So the -1 in the reshape, what this means is keep the shape, the first item in the shape, that's 600 items, keep that, and the -1 just means unfold everything else. I don't know exactly what it is. Well, I do know it's 784, but I don't want to think about that, so just unroll everything else into just one dimension. So when we do that, we have items that are 600 by 784, and the test data is 100 by 784. That's the 28 by 28 is 784. Yes?
Is there also a simple way to do the reverse of that?
To do to give it back? Good question. If I did test data 1D dot reshape, that would give me back the original shape. Does that answer your question? Or just take that shape and make it into that shape. I'm not sure what that shape is, but that's what I want. And that gives you back. It spit out this array out here because I didn't allocate it into anything. But that's okay. So we have the items that we need for training. Let's go on and build our neural network. So here's what building them all the neural network looks like. Let's call this model actually. Let's call it dense. Dense equals sequential. So it's a sequential model. So we start by initializing this object, and then we add items into this object. Dense dot add. We'll add a dense layer with 10 units and an input shape equals train data 1D dot shape -1. Yes, I think that's right. Comma. So this is the first layer. The number 10 here is an arbitrary number that I've chosen. So what I'm telling it here is into the dense model, add this object, a dense layer, densely connected layer. So every unit here will be connected to every one of the 784 pixels in the original image, and make 10 of those. So my first layer has 10 units that are all connected, each one connected to all the pixels. I have to tell it about the input shape. So this here I've given it a tuple. And this number here is 784. It's this number that I'm telling it about. Sorry, it's this number here, so there'll be 600 items of that. And then I have to tell it what kind of activation function to use. And I'm asking for the ReLU activation function that we saw yesterday. And then I'm going to add to that another layer, another dense layer. This layer will have 3 items in it, or 3 units in it, and it'll have a softmax activation function. This layer here is the output layer of this network, and it has 3 units in it because there are 3 classes of objects in this data set. So this number 3 is not arbitrary. It depends on the data in this case. And that's it. So this is a 2-layer network. It has an input layer that gets its input straight from the images. It has an output layer that tells us that kind of selects between. This softmax activation function is a different kind of activation function that operates on this layer. I won't go into too much detail about softmax except to tell you that it's a function that takes a number between 0 and 1, and it has the property that it looks over all the items in the value of that function in any particular unit in this layer depends on the values of the activation in the other units. And so it operates like mutual inhibition a little bit. If one layer has high activation and another has low, the higher will become higher, the high will become higher, and the low will become even lower. It kind of suppresses its neighbors. So it's kind of like a mutual inhibition operation that increases the contrast. You can think of that as increasing the contrast between different items and selecting which item will be the winner. And then when we look over those 3 numbers, we can choose which class we think this is by choosing sort of the maximal activation, the unit that has the maximal activation. Each unit here represents one of the classes, and we'll look at the one that has the maximal activation.
Why you chose 10 elements for that?
That's an arbitrary choice, and it's sort of a little bit of an empirical thing that you need to try out a little bit while you're designing these things. Here I chose 10 because it's a convenient round number. There really is no particular reason.
Would you be thinking in terms of the size of the input images when you do that, or the number of classes you're looking at, or what are the sort of thought patterns go into deciding 10 rather than 110?
Yeah, a little bit of both. It depends a little bit on the dimensionality of the original data and the difficulty of the task. The kind of thing that this will affect is how powerful is that layer in transforming things from one space to the other. You can think of every one of these layers, it's kind of taking the space of the pixels, and it's transforming everything, it's moving everything to a representation of a slightly different space. And if you have a lot of dimensions in that space, then you can do a lot of weird things with your data. But you want to do this depending on the difficulty of the task and the dimensionality of the original data. You want to build networks with a lot of layers to do this incrementally, kind of bit by bit, that operation. So in practice, this ends up being a little bit of an empirical. You try a few things out, you see how well the network learns, and you choose something where the network learns well. I should say something that I should have underscored a little bit more, and Russ mentioned in his talk, is that we have a strict separation here between training data and testing data. And if we're doing this in practice, we won't ever touch this test data until we're really, really happy with all of those kinds of choices, the learning rate, the number of layers, the number of units in every layer. We'll do all that only in all those selections will be done only in the training data. And then when we're really, really done, that's when we take out the test data and test, and we don't go back and say, oh, well, I think we could actually do much better. Let's go back and try again. You lock it in a safe, and you don't touch it until you're really ready for it. So, yes?
This may be a little bit too broad, but is there like a recommended minimum N for splitting a training and test set? Like you have to do, I guess, or is that just like?
Yeah, again, it's a little bit of an empirical question. I actually wrote a paper. It's currently only a preprint, but hopefully soon it will be a paper, where we took a data set. We had trained, my colleague Aaron Lee here in the ophthalmology department had trained a neural network of this kind that does classification to classify OCT images, retinal imaging, between patients with macular degeneration and patients who didn't have macular degeneration, who were healthy actually, their retina were healthy. And do that classification, and it turns out that the neural network of one of these convolutional neural networks does really, really well at this. And the question we were asking is, okay, how much data do you actually need to do this? So we split the data up into two and tried it again, and it did pretty well, and you split it again and again and again, and we quantified how well the network does as you split up the data down into smaller things. One of the problems that we've had in sort of convincing others of this is they look at this and they say, well, that's nice. It might be true for OCT images of AMD, but it looks like maybe it wouldn't generalize to, I don't know, brain images of ALS versus controls, for example, right? And I agree. It sort of depends on the particulars of a problem. Okay, so let me initialize this thing. So I've done that, so now I've created the network. I have this object that's the network. And the next thing that I need to do with the network is compile it. So that's a weird thing. You've learned that Python is an interpreted language where we don't need to compile things. But in fact, for this kind of thing, we need, as I mentioned before, there's sort of this computational backend, and that computational backend needs to do something like a compilation step on this model in order to design the program that it will use to run this. Yes?
Previous block, the second line, actually the second element, you say that we keep all pixels to the first layer.
Yeah.
Does this mean it's one batch?
Yeah, so in every batch, you'll see soon, in every batch I'll give it several rows from this matrix. I've reshaped the matrix, the training data, to 600 items. Each item is a single row in this matrix, and all the pixels are unrolled into one long, one-dimensional. So I've taken the image and I've unrolled it into a long vector of 784. And the network will get, actually in every batch, it will get maybe 10 of those rows of 784 items, and then it'll train those weights in that layer. Every one of the units has 784 weights corresponding to each one of these pixels, and we'll train all of those weights. Okay, so I'll just write this down: cross entropy, and then I'll explain loss optimizer. And then metrics. Okay, so we compile this so that the underlying computational backend can design the program that it will use, and we have to tell it a few things when we compile it. We have to tell it what loss function we'd like to use, and in this case we're using a loss function called categorical cross entropy. I won't go into detail again about exactly what that is, except to say that that's a very common function to use when you're trying to do a classification. It's a function that tells you how well you're doing in classifying things. And then we'll use an optimizer called Adam, so we need to choose the optimization thing. That's a little bit about how we step through that gradient descent, what strategy we use. It turns out there's a whole field of optimization that has come up with really, really interesting and clever ideas for how to step through this gradient descent problem. It turns out it's a really, really hard problem, especially when you're working in a huge number of dimensions. You can already start doing the math. There are 10 units here. Each one of those connects to 784 pixels. You can start seeing what the dimensionality is of these things. It's pretty large. And so that's this optimizer. And then we can ask for additional metrics that will be, accuracy is a little bit more intuitive than categorical cross entropy. So we'll also ask the network to tell us how accurate, just how percent correct in every epoch, and then at the end to report to us the accuracy. Keras takes that as a list of strings because you can have several of these metrics. Here we're only choosing one, but it always requires a list. So that's why it's enclosed in square brackets here. So I compile the model, and once I've compiled the model, I'm ready to train the model, to fit it. So this model has a fit method, and we give it test data, and we give it test data 1D, and then we give it the test labels, and we tell it to train with a batch size of 10, and we tell it to train for, let's say, 12 epochs. Again, these numbers are empirically, you should empirically derive them. Here in this case, I just made them up, to be completely honest. And then it goes and it does the training. So that was the training. So it tells us, here I am, that went really fast, so because it's a really small network and there's not a lot of data. Here's epoch 1 of 12. I'm going to have 100 steps here, and then it goes and says, oh, the loss is this number, the accuracy is 0.48. So it starts being pretty, it starts with the loss being, the accuracy being pretty low. It's basically not really a chance, because chance is 0.3, but at the end of the first epoch of training, it was at 0.48. By the time it finished epoch number 2 out of 12, it's at 83%, and it keeps climbing. And it keeps climbing and climbing, and it actually does really, really well by the end of this. What's the problem with that? Sorry, I couldn't hear. Maybe Amanda, right? Yeah, it's we're testing this on the training data itself. So it may be very, very accurate on this training data, but that wouldn't generalize to other items outside of this training data. So we'd like to actually do something a little bit more clever. In every step, maybe in every epoch, we'll look at some other data that hasn't been used to train the network, and we'll validate on that data. We call that a validation data set. Do you have a question? Yeah.
But with 7,000 parameters, we should have 100% accuracy, right?
We should have
100% accuracy. I guess there's more parameters in the model than we have.
Yeah, we might not have gone in far enough. If we added epochs, maybe eventually we would reach. I agree. Eventually we'd probably reach close to 100%, with kind of numerical accuracy and stuff, with that number of parameters. Absolutely, we have many more parameters than data points, right? Than actual dimensions in the data. So we should do. But so okay, so absolutely, this will overfit. So another thing that we need to do is to tell it, take out some of this data up front. I gave you 600 items. Choose out of that, maybe for simplicity of calculation as I'm standing here. Take 60 items, set them aside. Do not use those to backpropagate error at all, to adjust the weights. Instead, at the end of every epoch, just test the network on these 60 items, on this 10% that I've set aside. So this validation split does that automatically for us. And then if I run the fitting again, it'll tell me not only the accuracy, and then now it started from being trained because I started it where it was. It'll tell me not only the accuracy on the training set, but also the accuracy on the validation set. In this case, it's doing really well on the validation set. So this is working pretty well, actually.
No, because they already see.
Oh yes, I'm peeking here. You're right, absolutely. These same validation objects were in the training set in the original thing. I need to start over, clearly. So I'll just start from here. I'll reinitialize this object. Good catch. Yeah, that's the kind of stuff that, okay, so now validation accuracy is pretty bad. We start off again, we started off the network fresh. We initialized it with sort of some initial random weights, and then it goes to validation accuracy is 0.5, but eventually it does actually learn and it gets to validation. In this case, no peaking. This data was set aside in advance, and it's used in every epoch to test. And we can keep doing this same thing again and again. We can say, well, what if we had, instead of 10 units here, maybe we put 100 units. Would that make things better? That takes a little longer, just a little longer to train. And we can compare this validation accuracy. We can say, well, do we think this is better or not? And we can keep doing this again and again and again. Yes?
Is that using the test data instead of the training data?
This does not use the test data. I haven't told the network about the test data yet.
I think the code actually was
Oh. Sorry about that. That was just an error of typing. Yes. This is what I should have written all along. So yeah, so at this point I should not tell, okay, this is a slightly larger data set. Yeah, I should keep the test data locked just so that I don't do any of these mistakes. I shouldn't even like point to it before I do anything. So at this point I've done hopefully all the errors I can. You've seen everything. Yes?
So whenever you record the data, it will start from where you ended last time. But will it keep the same split of training and validation?
I don't think so. I think it chooses a new random split. Yeah. I think you can fix the random seed that is used for that splitting, and then it would do exactly, it would choose the same items to be training and split, or it would choose some kind of split, a new split. The important thing here for the validation purposes is that these are data items that the network currently isn't seeing to adjust its own weights. It's not using in that backpropagation process that I told you about. Yes, exactly. This is the proportion of items that will be set aside for validation. And so in every epoch, we only use this validation set, in this case, 12 times at the end of every epoch. We look at it 12 times, and we never use that validation. That validation step is never used to adjust the weights. It's just used in order to do this kind of accuracy and loss evaluation. Yes, more question. Ready?
How are the starting points?
There's a whole set of strategies to do that, and under the hood, Keras is doing the right thing for you. Yeah. Yes, back there.
How do you go about choosing your batch size and epochs? Is that something to play around with?
Yes. Yeah, I haven't seen anything. There might be work out there. I don't know all the literature, but I haven't seen anything that said, oh yeah, there's a rule here. If this is the number of items, this is their size, this is how many classes you're trying to classify, your batches should be this size. Yes. Back there, yeah.
Are there functions to automatically cycle through all of that, or do we just like enter in the number, like batch size and epochs, for example? Is there a function to automatically?
No, you'd have to write a little loop that would do that for you. Yeah, yeah. But at this point, I mean, the nice thing about Keras is actually this is a fairly small number of lines. You can compare this to, if you want, you can go and look at the TensorFlow documentation. Under the hood, this writes hundreds of lines of TensorFlow, which go into the tiny details. So this is already pretty concise. But yeah, it'd be nice actually to have systems and ways to automatically do this. One of the errors that I think the field at large does a lot is this peaking thing, right? Where we're working on something, we have some data, we train some neural network, we go and look at the test data, we're like, well, we could do better, let's go back and repeat that process again and again, and then that's sort of p-hacking. In these systems, it's much harder to actually reason about p-hacking because we have a lot more history of thinking about it in sort of the traditional statistics that people use in a lot of the psychology research than we have here. But people kind of know that this is, and there's a lot of what's called cargo culting of these kinds of things like batch size and number of epochs and so on. So right now the field, it's a little bit, you read some of the papers and you should ask yourself, when they say their test accuracy is 95%, did they separate these things properly? Did they do all the tests beforehand? How do we know that everything was done as it should be? Yeah?
So how do you know which activation function to use? I know people would trigger, but why not like hyperbolic tangent?
That's mostly for computational convenience. Yeah, yeah. And you can set this to be other kinds of things. Well, let me move on to the convolutional version of this. So I will say, you can, if you want to create a network, I'll just adjust this network a little bit. If you want to make a deep network, you can add another layer of densely connected things in here. Everything but the input layer doesn't require this input shape. Only the first layer needs to know about the input shape. At this point, if I add another densely connected layer here, now I have the first layer connected to the So now I have one layer connected to the pixels, and then the next layer is now connected to this layer, sort of an intermediate layer and an output layer. And that takes a slightly longer time to fit because there are more parameters and so on, and you get back all these numbers as well. So that creates, and you can stack those. You can stack those arbitrarily deep. So that creates a deep network, and then after all this has been said and done, you're happy with your architecture, you're happy with the number of batches you have, the number of units in every layer, and so on. You've reached what you think is going to be your maximal validation accuracy. Then and only then do you go and do evaluate on test data, 1D test labels. And that will tell you what your true accuracy, or give you an estimate of your true accuracy. This is called cross-validation. You'll hear more about that from Jake later this afternoon also. This is the value of the loss function, this categorical cross-entropy. As I mentioned before, these values are a little bit hard to sort of interpret because it depends a little bit on the number of categories and so on. And that's the reason we also want this accuracy in addition. Yeah. Okay, so I'll move on to the next little section where we'll talk about a version of this that uses convolutions. So I won't go into too much detail about convolutions. Michael yesterday in the section on computer vision actually described convolutions. I'll put up this really elegant picture that some people, not me, created that describes what a convolution is. If this is an image, this blue thing here is an image, then a convolution is done by taking some kind of array, a 3x3 array in this case, that we think of as a filter on this image, and then in every, sliding this thing along, and in every point taking all of these things, multiplying the filter by the items inside of the blue array. So you take this 3x3 array and you slide it over, and every point you multiply it directly, item by item, with the underlying image, and you sum all that together. And that sum goes into the output of this. And the reason I think of this as a filter is that you can do a variety of different filtering operations on the image. For example, you can design this kernel so that it will be sensitive to the location of edges in the input image, in the blue image, such that the green image here that we refer to as a feature map will tell you where there are edges of a certain orientation, for example. I'll draw that. It's actually drawn here. This is actually a drawing from yesterday's computer vision session. If we have low values here and high values over here, and the image contains low values on this side, in this particular part in the image, it contains low values here and high values here, the sum of these things, the match between, the correlation between this and the underlying part of the image will be high, and multiplying these and summing them will give us a high number. But imagine that there were high numbers here and low numbers over here. It would be the opposite. It would be sort of anti-correlated. And when we multiply and sum that, we get a small number. And if there's just a uniform field under here, then it would be sort of an intermediate between those. So what this tells us is how much of this kind of feature is in the image in that location. This is this convolution operation. And so one thing is, if you've learned during your studies about the mammalian visual system, you can start seeing that a convolution operation is a little bit like the operation that maybe a set of neurons in the primary visual cortex do. You can think of all the neurons that are oriented, or they're sensitive to a particular orientation in all the locations in the visual field. All of those together, if you looked at the activity of all of those things together, you could think of that as a convolution with that orientation. And so if you look at the visual cortex, you could think of it as a bank of convolutional filters. And so inspired by that, people who were working with neural networks back in the early 90s, Jan LeCun in particular, who was working with neural networks in the early 90s, said, oh wait, this is really nice. Instead of connecting every one of our units in the first layer to all the pixels in the image, let's design a unit that has only 9 weights. something like that. And that unit will really have only 9 widths, but we'll convolve the image with that unit so that when we're trying to derive the output of that layer, that output will be a feature map. It will be where in the image is there a match to these 9 pixels. So reducing the number of parameters per unit drastically. We're going down from 784 1 per pixel to this convolution. And part of the reasoning there was this works well, seems to work well in the mammalian visual system, might work well in an artificial visual system as well. And it turns out it does. So it learns, the systems learn certain kind of informative features. And if you look at the neural networks and you look at what kind of features they are sensitive to in different layers, it turns out that maps in a variety of interesting ways onto what our own visual system has somehow evolved to extract from the visual world. So let's see how we build a network that has these kinds of things, and I'll kind of recap, I'll reiterate some of these things that I mentioned now as I go along and implement this. Okay, so to do this we need to, in addition to the things that we've imported from Keras so far, we need to import from keras.layers a layer called conv2d and another layer called flatten. Flatten. And I'll import these. So I forgot the keyword import, so it was not syntactical. I'm importing 2 kinds of objects, conv2d and flatten. And now I'm going to build another model. This model will be a CNN, convolutional neural network. CNN has is a sequential model, so it's the same kind of thing as the previous one. It will be layers on top of layers sequentially. And then I'm going to add a first layer to that. That layer will be a conv2d layer with 10 units, kernel size equals 3. Input shape now is I mean, okay, that did not fit everything in one neat place. So this is our convolutional layer. I'm starting an object called a convolutional. Conv2d stands for a convolution in 2 dimensions. There's also a conv3d. If you have 3D things like movies or maybe volumes of data, you could use a 3D convolution. The kernel size here is the number, the size of one of these sides of this convolutional kernel. So they'll always be sort of isotropic. So 3 by 3. So 9 pixels in this case. And then we tell it about the input shape, about the shape of the data to expect. So train data.shape1 is 28. This is the number of rows in every image. Train data.shape2 is 28 as well, the number of columns. And then train data.shape3 is 1 is the number of channels. So we only have 1 channel. And we sort of omitted, there were 4 items in the shape of the training data. We omitted the number of samples. We don't tell it about the number of samples. It's only about the size of every single item, similar to what we did before. So we need to tell the first layer about that. Okay, the next layer is going to be a flatten layer. And it doesn't have any inputs. It's a flattening stuff. I'll tell you about that in just a second. I'll come back to this. And then the last one will be a dense with 3 and activation equals soft max. So this last layer here is our output layer. It's the same output layer as we had for the densely connected network that we had before. It does the same operation. It looks at its inputs, and it's connected through connections to every one of these units is connected to all of its inputs. In this case, all the feature maps in all of this first convolution, every pixel in every one of the feature maps in the first convolutional layer. And then it kind of sums up things from there and decides which one of the items was shown. The flatten layer, what the flatten layer does is it takes the outputs of the convolution, which are two-dimensional things that are like images. These feature maps are two-dimensional, and it flattens every one of them. You remember we did this by hand for our inputs to the densely connected layer. We reshaped our array. What flatten does is reshape the array in a similar manner, giving it a single row from every one of the inputs. So the feature maps get flattened into these long, flat things that then get fed to the, yes? What is? Dense. Oh, 10. 10 is an arbitrary number, the number of units in that layer. So we have 10 convolutional units. We have the option of creating different units. One unit might be sensitive to vertical lines, another one might be vertical lines, and another one might be sensitive to horizontal lines, or different features. So we'll create 10 different feature maps. Out of the image, we'll have 10 different feature maps. Now, if we did a convolution that preserves all of the pixels in the original image, we'll do the math in just a bit, and I'll show you the number of parameters. But I'll sort of set this up. We have for every unit in that, it has only 3 by 3 parameters, but its output is very large. It has the full 28 by 28 pixels, right? And previously, every unit had just one number that it was outputting. Now we're outputting 700. Each one of these units outputs 784, at least 784 numbers. Yes, approximately. So that densely connected layer is connected now to 784 times 10 things. That's a lot of things. Yeah. So I'll show you exactly the number for that in just a second. Yes?
When you say unit, is that analogous to a node in the diagram?
Exactly, yes. Yeah. Okay, let's build this network, and then we'll do a little. So we can build that network. We can compile it in a similar manner to how we compiled before. So just see loss, not cost. Category cross entropy optimizer equals atom. And then we'll ask for metrics equals accuracy. So we're asking for the same. We'll use the same loss function, the same. We're doing pretty much the same. And then CNN.fit with the train data. This time we're using the training data not flattened in the original dimensionality. Train labels, and we'll have epochs equals 10, batch size equals 10, and again, validation split equals 0.1. And off we go. As you can see, this is a little bit slower, and it reaches some validation accuracy. It's not too important to look at the details. Go up. Okay, here we go. So these are the 3 steps. We construct the model, adding layers into it. We can add more of these convolutional layers, making this thing deeper as well. And we'll see this in just a second. And then compiling, fitting, and then once we're done with all the fitting options, building all the different architectures we want to try with all the different numbers of units, numbers of layers, batch sizes, epoch numbers, etc. Once we're happy, then we take out our test data and we test it just once to tell us, to use the evaluate function of this model to tell us how well does that give us a fair estimate of the accuracy of this model. Yes? That's also done in this compile step. Learning, let's see. Here we go. So these are the keywords. it might be so, this gets trickier. You can, as an optimizer here, you can give it a string, which is the simple version, or you can give it an object, which is an optimizer. So I believe there's a, from Keras.optimizers import Adam, right? You can create my optimizer will be Adam with here. This is the default learning rate for Adam, but I can say, oh, I want a faster learning rate. I want learning rate to be, well, maybe I want smaller. Usually I want smaller. -7 for the learning rate, and then instead of giving it a string here, I'll give it this object. So it takes either the string or the object, and then so now I need to initialize this thing, and then so now this is what would happen with this other learning rate. Did it do better? No, it did exactly the same. So maybe learning rate doesn't matter for this particular problem. And this problem, I should say, everything I'm doing here is a little bit contrived because the size of the data is a bit small. The networks are all pretty small. This is a toy example. The examples you're likely to encounter in the real world are going to be bigger and more complicated, and learning rate is going to sometimes matter, sometimes not. So you can see there are a lot of things you can try. That's part of the problem. Can end up with these big grid searches over all of these different meta parameters. It makes things interesting. So okay, let's do a little bit of a comparison. I'll go back here and I'll set this to be 10 here and 10 here, so that I have a fair comparison to another convolutional network. I'll change this convolutional network so that it has another conv2D layer with 10 with a kernel size of 3 and activation as ReLU. So I have two networks. They have each has 2 layers of different kinds of units. One are densely connected units, and the other are these convolutional units. I've made some. Oh, I need to do CNN.add this thing. Okay. So now I can go and compare those two. CNN.summary, not summarize, summary. Will give me a summary of the network. So this is a nice, useful little function that Keras provides that gives you a summary of the network. So what you can see is that it actually doesn't preserve all of the pixels. This is because when you convolve something with something, you have this you have the problem at the corner of the image. If we're right at the corner of the image right here, there's nothing to move out unless we pad around with zeros. So you can pad around with zeros, but we haven't done it here. So we've started, our starting point is cutting off one strip of pixels off the side. So our next step is actually 26 by 26 pixels in size. That's the output shape. And then we're stripping one more, because we're doing this twice, one more layer, 24 by 24, and so on. And this is the number of parameters. So I'll explain this number of parameters. The number of parameters here is 10 units that we have times 9 pixels in the kernel for every one. That's 90. And then there's another thing that I haven't mentioned until now, but I will mention because it adds to this, is that every one of the units also has what we call a bias term. You can think of the bias term as being where this nonlinearity is relative to where the threshold is. You can think of it a little bit as where the threshold is. And each one, so we adjust there's one more weight that we actually adjust per unit that has to do a little bit with the threshold of activation of this unit. So that gives us 10 more parameters here, so that's 100 parameters. And then here we have, what is it? So there are 9 units, there are 9 pixels. There are 10 units, and they each one look at the outputs from each one looks at 10 different feature maps from the first layer, right? So there's 10 feature maps times the 10 units times 9, that's 900, and then 10 bias terms, that's 910. This number here comes from flattening the 10 feature maps at this stage. So it's 24 by 24 by 10. Yes, 24 by 24 by 10 comes up to this number. And there's no additional parameters here, but the output is 5,760. And then by the time we take 3 and connect each one of these 3 things to all of these 5,760 things, we have on the order of 17,000. There's 3 additional bias terms there, hence this 3. So we end up with this total number of parameters in the network. Comparing that with the dense network, dense network has, so here this is 10 units times 784 pixels plus 10 for the bias terms. The next dense one actually only connects to, there are 10 units that connect to 10 units each. That's just 100 parameters. That's pretty small. And then at the end, we have 3 units connecting to 10 units. That's 30 plus 3 bias terms. So that's 33. So the number of parameters here is actually much smaller. But you'll see that the networks have a little bit of an upside down, in terms of the number of parameters, a little bit of an upside down structure. This has very few parameters up front and a lot of parameters at the top. And this has a lot of parameters up front and fewer parameters as we go. So they have slightly inverted structure. One way to think about it is that these convolutional layers are really powerful in terms of extracting interesting stuff. So they don't need a lot of parameters, but reading out that information requires a lot of parameters. Now we need a lot of parameters when we go to this final layer to interpret the output of all these convolutions. So that's one way to think about that. Okay, so this is the basic thing. This is how we basically construct convolutional neural networks. There are a lot of things that we can add on top of that, and I'll show you just a few things that you can do in addition to the things that I've shown so far. One thing that you might want to do is you might want to deal with this explosion of the number of parameters in some way by somehow getting all these parameters under control a little bit. And one strategy that people use in order to get the number of parameters under control is pooling. So from those feature maps, those intermediate representations, maybe we don't need all that resolution. If we want to know if our first layer is detectors for where there are edges, maybe it's enough for us to get a kind of a low resolution sense of where the edges are. And so pooling is a good way to do that. The idea behind pooling is it's sort of like a convolution, but it does just one operation. So it takes 9 pixels, or often 2 by 2 pixels, and out of those 2 by 2 pixels, it selects the maximal value, and it turns those 2 by 2 pixels into 1 pixel that has just the maximal value in those 4 pixels. So it takes a feature map that has, say, 28 by 28 pixels, and it reduces it in dimensionality by a factor of 2 on each dimension. So we have a feature map that's 4 times smaller than what we started with. If we do a pooling on little windows of 2 by 2 pixels. So the way that is implemented in Keras, let me start implementing a new network that has this feature, CNN pool equals sequential, and then I'm going to add a conv 2D layer. I'm going to have 10 units again. Kernel size equals 3. Input shape. Let's just cheat here and just hard code that. 28 by 28 by 1. And then activation equals rel u. And then cnn.add. Oh, I need to, before I go into this, I need to do from Keras dot layers import max pool 2D. It's another kind of layer that does this pooling operation that I just described to you. So I'm going to add a max pool 2D thing, and I'm going to give it the number 2. 2 means I'm going to pool over little boxes of 2 by 2 pixels. So when I get the output of this thing, which was 24 by 24, what was it, 26 by 26, I'd like you to take little boxes of 2 by 2 and give me back the maximal value in every little region in that image, but give me back only 13 by 13 pixels, much smaller thing. So that's this thing here. Let's add another one here, CNN. Oh, I need to add this to my CNN pool, not to the CNN. I'll do another 10 units so that it's the same size so I can compare them. 3 activation equals rel u, and then CNN pool. Pool 2D. So I'll pull over the outputs of these as well. I'll reduce the feature maps of this one as well. So I'm doing this operation twice, and then CNN pool dot add flatten. So I'm flattening the output of this. So there's one convolutional layer, it has its feature maps, those get pulled and fed into the second convolutional layer. The outputs of the feature maps from that one also get pulled, and that output, the pulled output there, gets flattened as input to this last dense layer up here that has 3 units and an activation equals to soft max. Okay. Good, so I've created this one, and let's take a summary of that one to get a sense for what's happened now. That was the wrong one, CNN pool. Here we go, okay. So as you can see, there's the first layer. It has, the output is 26 by 26. Again, the number 26 comes from the fact that the convolutions go all the way to the corner, but they can't go beyond the corner. So we were kind of peeling off a layer at the end. So we have 26 by 26. A max pool operation has reduced that down, the feature maps from 26 by 26 down to 13 by 13. A second convolution on this peels another layer off the ends. So we get down to 11 by 11. We pull that down further, down to 5 by 5. And so now when we flatten, we have an output of 250, which means that the last layer would only have 753 parameters instead of the 17,000 something parameters that it previously had because of this pooling operation. So we end up with a fairly small number of parameters, smaller than the equivalent densely connected network in this case, and much smaller than the convolutional network that didn't have these pooling operations. So maybe that's a good thing. I'll just say maybe because, again, it's an empirical question that depends a little bit on what you're doing. But this is a nice trick in case you think that you don't have enough data, that maybe some of the features are actually larger than your small convolutions, that it doesn't matter that much exactly where that edge is. If there's a little bit of, if you can afford to downsample your feature maps, you can do this and get a model with less parameters. And then compiling and fitting this model is the same as before, and evaluating the model would be the same. You would try this one in addition to all the things that you've tried so far, and then once you're really happy and you think, oh yeah, I do need this pooling thing, then you would test it on the separate test set. What questions do you have about this, or anything really at this point? Yes? Go ahead.
What if the labels are high dimensional as well? So what it was mentioning in Slack, possibility of predicting execution in one part of the brain from another part of the brain. What are the
Yeah, so there's, in addition to these convolutional networks that I've shown you so far, so these convolutional networks are actually a little bit of a merge between convolutional networks and densely connected, right? Because at the end here, we have a densely connected thing that kind of takes the image and ignores the fact that it has a spatial structure and just reduces that down to 3 numbers, right? But you could, in the end, have a convolutional layer, and the convolutional layer would give you an output that is an image, or this feature map, right? A single convolutional filter that just gives you an image. And you can compare that image to another image. One thing that people have done, and I think Sage, who might be in here, there she is, did in the poster that she was presenting yesterday, is segmentation using these networks. So in segmentation, you can't end up with these 3 numbers that tell you. Instead, you need to know where. So you need, for every pixel in the original image, you need to know, is it inside the object of interest or outside the object of interest? So that's the simple case of sort of binary segmentation. And for that, what you need is a network that is convolutions all the way through. So now you end up with a proposed segmentation. You end up with an image that has zeros or ones. You can kind of do, the trick a little bit is to do softmax in every one of your pixels and choose between 0 and 1. And then you take that image and you compare it to your true segmentation, and then you can compute some kind of error. In this case, we computed an error called the categorical cross entropy for segmentation, and it's very typical to compute something like a dice coefficient, and then propagate back the error from the dice coefficient back all the way. And Keras makes it fairly easy to build those. If you're interested in implementations of those kinds of things, I have some Keras implementations of that segmentation network, for example. I have an implementation that shows you how. And there's a lot of literature on how to do this. One of the things that is nice about Keras is that you can start building. You can imagine how you'd write, instead of this half a dozen lines of code, you'd write 30 lines of code that would do fairly complicated things, connecting different things to each other and so on. Okay, what other questions do people have? So I think these kind of fully convolutional networks, if you wanted to, for example, this idea that Aya brought up in Slack for, I think a fully convolutional network would be the sort of the direction. There are much more complicated things you can do. There's a whole field of sort of image synthesis that does really wacky things, like there's something called the adversarial networks, generative adversarial networks, where you have two networks working against each other. One tries to generate images using this idea of fully convolutional, and the other network tries to tell whether the image is real or not. And that second network gives feedback to the first network to tell it whether it did well in generating a fake image or not. And that turns out to work in all kinds of really interesting ways to generate images that never existed in the world before. And to do things like style transfer. You can ask a network to generate an image. You give it a photo and you ask it to generate something that would look like a Picasso generated out of that thing. And it turns out you can do all kinds of things like that. Okay, one more trick then. I'll tell you about one more thing that you can do here to improve these networks. One of the worries that you have with this number of parameters that we have in these networks is that the networks will start overfitting really quickly. You might worry that a lot of your units will become highly correlated. They'll see some set of images that have some kind of features, and they'll really become correlated with each other. And a trick that people have come up with is to think of the network, or rather maybe I'll phrase it a little bit differently, is to, in every training step, to sample a subnetwork of the original network and train only that subnetwork. So the way that is done in practice is you silence a few of your units every time. You drop out a few of your units. So let's say that we want to apply this idea to this first layer here. We would tell the network, so we would import another kind of layer called a dropout layer, and we would add a dropout layer here, with, say, 25%. What that means is that in every step of learning, 25% of the units in this first layer would be ignored. They wouldn't be used in the forward pass through, and they wouldn't be, their weights would not be adjusted in the back propagation. So with every sample of training, you're ignoring some of these weights. You're sampling from this network a subnetwork that has only some of the units. Yes?
Is that sampling randomly, or?
Yes.
Okay.
Yeah. We'll sample randomly every time. Yes?
Sample the entire convolutional unit, or just?
It'll sample specific convolutional units. So say we have 10 here. It'll choose, I think in this case, I'm not sure if it'll choose 3 or 2, but it'll choose one of those. Let's just go with this because that's simpler. It'll choose 2 of those and it'll ignore them. It won't use them in the forward pass, and it won't train them on the back propagation pass. Yes, it'll just ignore that entire node. It'll drop it out. And it chooses randomly every time. It chooses randomly different sets. And what's nice about this is that different parts of your network are seeing different parts of your training set in every pass through. And if there's some way in which seeing the same items would kind of correlate the units, you're neutralizing that a little bit by doing that. So that's called dropout. I'll add another dropout layer right here, and then we'll summarize that. you can see there's dropout. It doesn't change the number of the size of the output effectively, although in every iteration it does, because this will be 8 instead of 10. Right? So that's another little trick. I'll just show you one more thing that I think is really useful to know, and then we'll take a little break for coffee and come back. But let me just show one more tiny thing, and that is when you're doing this, often you'll want to be able to monitor the training, and that's done by, so if we fit this model that we just created, and instead of, so we have CNN pool, this model that has dropout and max pooling, and I train it, fit to train. Oop. And I split away 20% for validation appropriately, but I've assigned a variable out of this training that I'm calling, well, let's call it training because I keep saying training. So this thing here called training is going to store, runtime error, what did I do? Oh, compile, yes, I need to compile this model. Okay, so now it's training. You see this takes a little while. What did I do? Oh, I did only one batch of training. One epoch of training. That's fine. Let's go with that. Oh, actually, let me add some epochs. It did the default thing, which is to train just one epoch, because I didn't tell it how many, but okay, now I'm doing. Okay, now you can see it takes a little bit longer because it has all these convolutions and all these things that are more complicated operations, but it's done, and now I can look at this training variable. It's this weird history object, and that has in it a dictionary called history, which contains the validation loss in every epoch, and the validation accuracy in every epoch, and the loss, the training loss in every epoch, and the training accuracy. Let's plot some of these. So plt.plot training history. So I'll plot in one color the loss, and then in another color the validation loss, and I'll just I'll use this marker dot, and this additional input here is what kind of marker to use in presenting this graphically. So you can see is that the training loss on the training data, this blue curve here, is the loss on the training data, on the training data itself, keeps going down and down and down. And validation loss starts a little bit lower because we only actually estimated at the very end of the first epoch after some training has happened, but kind of flattens a little bit. I mean, if I trained, let me do something and show you what happens if you train for, let's think, 40 epochs. This will take a little while to run. What I'm trying to demonstrate to you is the fact that there is going to be an optimal point in terms of validation where you would like to stop. And we can see that using these curves, we'll be able to see exactly what that point is. Hopefully we'll be able to see that. It's done, yeah. Okay, so now when I plot these will have a longer, there'll be a longer history here. Okay, yeah, you can see that after a few, this is actually not a very typical situation. It has to do with the fact that these are there's actually not enough data here, so it does a few crazy things. It starts going down, It has to do also with the fact that I used the same model again. I'll correct that. Let me start again here. So I did the same thing where I trained another model again. Okay. So wait a little bit. What I'd like to show you is how validation goes down and then it goes up, basically. And that's a clear sign of overfitting to the training data. And you'll see this a lot of times. You'll see this kind of behavior. It shows you how important it is to have this separate validation data, because the training loss, almost per definition, can only keep going down. You'll just get more and more accurate on the training data, given the number of parameters that we have here that is larger than the dimensionality of the data. Well, it didn't quite do that, but you can see that it kind of flattens out. The loss also kind of flattens out. At some point, it just reaches as low as it could possibly go. Often what you'll see is the validation loss go down and then start going back up. And what that would tell you is a little bit about how long to train your network. But there are in fact ways for you to store the weights in every epoch, and then tell the network to store the weights for the best validation loss. You can tell it, I want the weights as they were when the network was at its best in terms of the validation loss. And those are the network weights that you'll use for inference then. You won't use these, let's say that this went down and then up. You definitely don't want to use the weights up here, because they won't generalize to a separate test set. You know that they won't generalize to a separate test set. So that's a little bit of how you monitor this. And in the notes for this material, there is actually code that shows you how to store the weights and reload them into a network. So you can store the weights into a file and then load them into a network that has the same architecture. Okay. What questions do people have at this point? Yes?
Obviously you can't see everything that's going on, but are there any visualization commands where you can zoom out and see what it looks like?
Yeah, so in the notes, again, there's a little bit about interpreting the results. One way you could do that is you could take the convolution, you could pull out the convolutional weights, and you could take an image and run a convolution of those weights with that image to see, oh, hey, this particular kernel likes vertical edges. So that gives you a little bit of interpretation. There's a lot more sophisticated methods to do that as well. And there's a really nice paper by Chris Ola and colleagues. I think I linked to that from the notes that talks about these methods for interpretability and visualization, in particular visualization of what a neural network is doing. Yes? Sorry, say that again?
If you want to force a layer to detect vertical edges, is there a way to force that?
Yeah, I think you can freeze certain, so you can, a trick you can do, you can say, well, I know that there are all these methods in computer vision, like say I want Gabor filters. I want my first layer to have Gabor filters, because the visual system has something like Gabor filters. I just want it to have that. You can load those weights into that layer, and then you can freeze that layer in training, so it doesn't change at all. Only the rest would change. There's a method called transfer learning, where you take an already trained network and you train it further on some other data set. For example, you might take some architecture that somebody has trained on ImageNet and take all those weights and chop off just the top and then retrain just the densely connected layer at the top to make some other classification, right? For example, Anisha has done work where she did exactly that for classifying between images that are of good quality, MRI images that are of good quality and MRI images that are of poor quality in large data sets. She took a pre-trained network that was trained on natural photographs of natural objects and just retrained the top of it. Turns out that network is a pretty good feature detector, even for images of MRI, of brain MRI. So yeah, that's transfer learning. Okay, I think let's take a break now. It's exactly 10:30, so let's take a 10-minute break. 10:40, come back here for the next little section. All right.